Okay, grade 11. So now we're going to take everything we know about graphing with slope-intercept form, and our m, our slope, and our b, our y-intercept. We're going to take everything we know about that. We're going to take everything we know about inequalities, and we're going to join them together to graph linear inequalities. Okay, so this first page, it's asking us to see if 3, 1, that point on the graph, is a possible solution for any of these linear inequalities below. Now we know that every ordered pair is an x, y, correct? We have practiced this in our 6.0 review. So that in any of these linear inequalities, if we insert a 3 for x and a 1 for y, we should be able to see if it makes the inequality true or not. So let's go ahead and do that. In A here, I'm going to rewrite this inequality as 13 minus 3. Now instead of the x, I'm substituting in a 3, is greater than 4, and instead of the y, I'm substituting in a 1. And now we're going to solve that. So 13 minus 3 times 3 is 9, is greater than 4 times 1 is 4. 13 minus 9 is 4, is greater than 4. Is that true? No, not true. Therefore, we can say that 3, 1 is not a solution for that inequality. It does not satisfy that inequality. Okay, what I would like you to do is pause here and figure out or do yourself B, C, and D, and then compare your answers when you press play to mine here. So you can see that in B, we see that negative 3 is less than 3, so 3, 1 is a solution. In C, 4 is less than 10. Yes, that's true. Therefore, 3, 1 is a solution. And in D, 1 is greater than 9. No, that is false. 3, 1 is not a solution. Okay, so you can see how we can test any point on a graph by putting it into a linear inequality to see if it is part of the solution or not. Okay, moving down. With example number 1 here, we're going to get our first taste of graphing a linear inequality. Okay, now we have graphed, as we've practiced the review for this unit, and so we are going to, number 1, here it is, put the equation into slope-intercept form. Then we're going to find the slope and the y-intercept, plot the y-intercept, and count the slope up or down from the y-intercept. Okay, so let's look at this now. First of all, putting this into y equals mx plus b form. We are going to move the x to the right. That will give us 0 x's, and we'll have 5y is greater than or equal to 2x plus 10. Remember, the 10 is positive, so I'm going to put a plus in front of it. All right, now we need the y on its own, so we're dividing everything by 5. And y is greater than or equal to 2/5 x plus 10 divided by 5 is 2. Okay, now we're good to go. This is in y is greater than or equal to mx plus b form. And we can identify our m, which is 2/5, and we can identify our b, our y-intercept, which is 2. So this is all stuff you've done before, and now I would like you then to plot that on this Cartesian coordinate plane. You can press pause. You're going to need to draw the x and y axes first. Okay, hopefully yours looks like this. I have plotted the b of 2, and then I rose up 2 and run 5 to the right. Okay, here's what it looks like when we join those 2 points up. Now, we have graphed the equation y is equal to 2/5 times x plus 2. We know, however, that this is not an equation, is it? This is an inequality. Y can be greater than or equal to 2/5x plus 2. So y can be greater than or is greater than or equal to this line we just drew. This line here is 2/5 times x plus 2. Now, we need to shade on one side or the other of this line to show that y can be greater than or equal to the line. So, how do we know? We look at the line and we say which side is y greater than this line. Okay, so you can ask yourself, some of you can just see it by looking at the y-axis, and some of you will need to think about it. So if we look at the y-axis, we can say here that y is 3 here. This is where y is 1. Which side is y greater than the line? Well, we can see it all above. Y is greater than all of this. And I'm going to do a neat job of shading. You will need to also do a neat job of shading. And we realize that this shading goes in all directions above this line onto infinity. Is this line also included as part of the solution? Yes, because we see that this is greater than or equal to y. Okay, now, there's some specifics about graphing here that we haven't discussed. I would like you to experiment with graphing inequalities using Desmos. And I want you to notice the way we draw the line, whether it's solid or dashed. That's one of the things, and we'll explore some other things together as you're doing it. So I'd like you to get out Desmos, and then we will do this page together. Follow these instructions here, please, as you compare these 3 graphs. Pause it while you do so. Okay, now, to answer these questions, why is the graph of the line called a boundary? Well, we can see that the graph of that line is the end of the inequality. So we're going to use that line to shade one side or the other. And that line holds the possible solutions in. It's the end or the boundary of all the solutions for the inequality. Why is the graph of the line sometimes dashed and sometimes solid? Hopefully you explored that and you realize the dashed line comes from when we have a greater than or lesser than. When we draw a solid line for a boundary, that means that we also have an equal to, so that the part of the solution can be on the line if it's solid. And when it's dashed, the line or the boundary is not part of the solution because it has to be less than or greater than the line. Okay, turn the page. Here we have some vocabulary, and I would like to use your textbook to fill that in. You can also use these graphs along the side in your notes to draw a line to the vocabulary that it describes. So, for example, we have the words continuous and discrete. Well, you could point to which is which on these graphs. Okay, pause and fill those in, please. Now let's just step through this graphing linear inequalities. You're going to notice that the first numbers 1 through 4, those are the exact same back here on slide 2 when we were graphing a line. Okay, we just have added 0.5 and 0.6. So once we graph the line, that is all the instructions or the steps up to number 4. Then number 5, we draw that line, either solid or dashed. And then number 6, we shade the solution region, and we shade it according to whether it's continuous, which we use a green color, or discrete, which we use an orange to represent discrete And remember that discrete is dealing with whole numbers, and green, continuous, deals with real numbers. Okay, let's move on and try a couple examples. Here we're asked to graph x plus y is greater than 4, and we can see that x is a member of all real numbers, so all decimals, and y as well is a member of all real numbers. Okay, let's put this linear inequality into our slope-intercept form, which means that we need to move this x to the right side of the equation. And so now we have y is greater than negative x plus 4. See this 4 here, it's a positive, so we write a plus 4. Okay, from there we can see that m is a negative 1 over 1, and b is a positive 4. Pause it, please, and graph that. And if you're comfortable joining that line with either a dashed or a solid, you can do that part too. Okay, the y-intercept is 4, so I plotted that, and then I rose 1 downward and run 1 to the right. Now I'm going to join those dots, and I'm going to join them now with a dashed line, because here we have a greater than sign. It is not equal to, so it's going to be a dash. Good. Now try to make that line as long as you can. Extend it quite a ways on your grid. If we flip back to the steps here, we just did number 5, drawing the boundary line, and we drew it dashed. Now we need to do number 6, shade the solution region on the correct side of the line. So here we are looking for, if I grab my highlighter again, sorry, we're looking for everywhere where y is greater than the boundary line we just drew. So we see that y is greater than on above the line, and I'm going to use green to shade it because we're using real numbers, meaning that this is a continuous solution, meaning we can use all decimals, everything between these grids, and it should look like that. So now, what does this mean? Like this green part, we call this green part our solution region. Solution region. What it's telling us is if we pick any point, we could pick this point, which is 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we could pick this point, which is a decimal, 1, 2, 3, 4, 5, 6, 7, 8.5, comma, 1.5. Any point that we pick in this solution region, if we put that in for x and y into our equation, it should make the inequality true. So let's just do that. I'm going to put 1.5 in for y is greater than negative 8.5 plus 4. 1.5 is greater than negative 8.5 plus 4. And yes, that's true. Anything you pick in here will make, in the green solution region, will make this inequality true. If you picked a point from out here, outside the solution region, it would make this inequality false. Okay, you have one graph here. I would like, no, we're going to do it together because it's a story problem. We're going to do it in a second video. You can open that second video up when it's time. We also have this equation to talk about, and we'll do that also in a second video. Okay, pause or stop here and open up the next video.